And we are back with an empty file. So let me just tutorials. Well, the tutorial files are available for anybody in the support center. So if you go for the support, like that page, use your credentials to log in. Ooh, I got some credentials saved. That's interesting. Ha 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 ha. Okay, seems like I saved the wrong password. But still, if you go into support center and yeah, then log in, the same page where you download STAR-CCM Plus, you can download the tutorial files. Then you get a folder that looks like this, and it's quite big, I'd say. What is it? No, paste. Here we go. It has like 40 gigs once it is unzipped, so it is kind of huge. But it contains 800 pieces of 800 files. So, what shall we do? We should import something from it's heat transfer and radiation. And then it should be here. It is our file. Nice. So we are importing that one. Let me just adjust my window so I can see this one on the side. Last time I found a sweet spot for the tutorial. Yeah, like that. Because we don't want to see what's next. So file, import surface mesh, and then I go to documents, CFD, tutorials, heat transfer and radiation, graphics card, and enclosure. Here we go. Do we want to no part contacts? Okay, interesting. Yeah, this time we want to open a geometry scene. Normally I don't do it because you just import several things. Ooh, interesting. So we have a case right now here. We got to switch. The first thing I always do is saying, okay, color mode goes to distinguish inputs. Because, yeah, then you can distinguish your inputs. And I should save it. Not open. I should save it. Documents, CFD, new folder, graphics card, and I call it graphics. Come on, GPU 01. Here we go. So yes, done that. Importing the geometry. In the visibility toolbar. Should I import it into 3D cut? Yeah, did that wrong. Okay, nice. Let's delete them all. Delete. Here we go. And delete the scene. We can keep the scene. So file, import 3D CAD into things. Go for tutorials. And then it was heat transfer and radiation, graphics card, and enclosure. Here we go. No contacts. Okay. Creating and visualizing contacts. In the visibility toolbar, select this one more and activate all edges. All edges, here we go, yes. Create part contacts. In the 3D CAD tab, select all body groups. Ooh, that's a lot. Did it. Right click, 1, and say Boolean, imprint. Imprint bodies. Okay. Select OK. The default imprint options are acceptable with it. Contacts are created for all coincident faces which satisfy a tolerance of 1e minus 8 meters. That's crazy. Okay. Okay, let's go. Inspect and locate potentially missing contacts. In the 3D CAD tree, right click the features. Yeah. Features imprint here. And say show contacts. Oof. This is what I wanted to see. Definitely. Contact. Okay. Show contacts. Okay, we want to show contacts. Right click the first imprint one. Nope, that's not what I wanted to. Right click the first imprint one object. That one. Yeah. Guys, I'm not seeing it. Can you spot it? Contact display options dialog. Right click the first imprint. Okay. Select search selected features for contact. Ah, here we go. And then additional. I need to go for here 0.5 and then say search. Okay, it searches, it searches. We are searching. So now first we have searched all the contacts that are within 0.0 something. No, e minus 8 meters, and now we are checking for everything in the range of e minus 5 meters. So we're going a bit coarser. Okay, that's interesting. Mm-hmm. All coincident faces on the imprint feature. Any coincident faces between PCB and memory chip. There's a missing content. Select all groups contact. Yeah. And create filter. And then cancel. Close. Yeah, I guess that's just closing. Close window. Okay, so now in the 3D CAD tree, right click on design filters. And select imprint faces. Imprint type, tolerant edges. Okay. Multi-select. Okay, there's another one. Okay, nice. And say show contacts. That's interesting. Create a fill. So right click on the selected nodes. You can also, is it here? Just a second. No, it's not here. Okay. In the visibility toolbar. So this is the visibility toolbar. Where is it? Ah, here we go. Oh, I can't see it. Damn. I did what you say, but didn't work. Okay. Skill issue, obviously. So in the contact display options, click filter. Filter body name contains plus PCB. Okay. Okay, filter again. Contains PCB. Apply. Contact display options. Okay. So memory chip 7 and here we go. This one is it. It's that one. Okay, right. Click. Okay. Okay. Oh, I don't see it. Ah, that's the two parts, I guess. Right. So this is the PCB and this is the memory. Okay, nice. Going on. Isolate selected contact pairs. What the hell? Oh, this one. Oh, okay. Ah, here we go. These two are the ones that we want to see. Okay. In the contact display options, we say close. Then we say update 3AD card and close 3AD card. Ooh, finally done. Good. Next one. Ooh. Defining regions layout. Oh boy, I need to see this. Thank you. So 3D CAD model, new geometry part. Create, yes, we want to deactivate it. Oops. Okay. Right click the parts air case and click OK. So now we have parts. That's our air case. And say assign parts to regions. Nope. I personally want to split this one for faces. I need to split. There is different faces, but I want to split by angle. So we are doing something different here. So we put that into the surface display here, so we can finally see something. Come on. So we have these faces now. We might need them later, but I think it's quite useful to see something at that point. So we are setting this, assigning it to a new region. One region for all parts, yes, of course. Boundary for each part surface. No, we're not doing it. Contact mode. Create contact mode interfaces from contacts. Yes. And we say apply. And we say close. And the thing is, what they now created is a region here. And the thing is, it has several boundaries. So it needs an air inlet and an air outlet. Part surfaces. We need. Oops. Where are we? What? Oh, holy moly! It created some parts. So inlet. And here we go for outlet. Okay. Okay, so we want now to select everything else. should we have... Oh boy, these two must have been in the same region. We are deleting the region again, come on. So we're taking these three here. Put them into this. Do they have... let's see them partly transparent. Yeah, I guess I don't need anything else special for that. Okay, we can just make this and say assign parts to regions and create contact mode interface that it said it wanted. Create a boundary for each part. No, it wanted each part surfaces, right? One region for all. Boundary for each part surface. That's going to result in a horribly lot of... Yeah, let's do this. Apply. We have 700 boundaries now. So everything from the faces will be deleted now. Because that will all go in one boundary. That was a bit of an issue. Deleting them. So our case faces. Zack, here we go. Bam. I want them later. Okay. So that's where we should be. That's nice. Create a region for all solids. Nice. Assign parts to regions. Okay, these three are not in there. Create one region for all parts and enter solid components. Solid components. Yeah, I did. Oh, the other one should be called air. Boundary mode interfaces. Okay. Oh, damn. Oh. Should have worked. So, air case, air inlet. Rename the interfaces. Yeah, doing that. New name, case fan. Air solid components. Air solid. Air solid. And capacitor 1 to PCB. Ah, maybe I should have called them all that. Okay. I guess I'm just taking it like that for now. Okay, I'm saving the simulation. That looks nice already. Hi, AAA1029. How are you doing? So, yeah, let's go. Continuum for the solids. Yeah, let's. That's gonna be the air. Nice. Let's create some continua. So this one is solids. So it's three-dimensional. Yes, it's multi-component solid. It's multi-part solid. And it's segregated. It's steady. And it's segregated solid energy. It's constant density. Okay, nice. So, yeah, looks like that. Okay, then we make some multi-select mixture components. Oh boy, what do we need? ABS. Any four materials. That's nice. Do we have silicon, by the way? Okay. Okay, cool. Close. So, naming that aluminum. Next one is ABS. Then we have alumina. And we have silicon. Refresh. Reorder. Yeah. It's interesting. Sometimes they are writing it with an I, like the British do, and sometimes they are writing it without an I, like the Americans do. Okay. Let's go. ABS, material properties, density 1050, specific heat goes to 2050, thermal conductivity goes to, oh, we could simulate a thermal paste here as well. Yeah, that's a story for another day, I guess. 2.5. Okay. Yeah, aluminum, material properties, density. Yeah, that's right. That's a bit worse, but thermal conductivity. That's interesting. People, did you see that? It's a different thermal conductivity for aluminum, because the original one is only valid for extremely pure aluminum. And once you just put a single bit of alloy into that, your conductivity instantly goes down by 20%. Alumina, its material properties, constant density. What did I choose here? I get, oh, it was gold, wasn't it? So it's 3960. Specific heat goes 850. Thermal conductivity goes 30. Interesting. And silicon. Silicon density, right, is there. 700 is there. 124 is there. Save. The PCB is constructed of layers of FR4, laminate and copper. Add a material. So making this one. Right click solids and say select mixture components. Okay. So this one is FR4 plus copper. Material properties. Density constant. 33. What the heck? Okay, interesting. And specific heat is 37 joules per kilogram. And thermal conductivity, oh, method. Orthotropic. Now we have different. K11 constant. 10. Hello. Please be. Okay, cool. I was too dumb. 10. Next one is 0.5. What the hell? And 10. Okay. So we have different conductivities in different directions. So this one, I guess, is the middle one was in the normal direction to the PCB, and the other ones are in yeah. Okay, nice. Next one, continuum for air. That shouldn't be that difficult and that much work. So new physics continuum, and that one, whoop, what did I do? Hit my keyboard. So this one is air. Yeah, hit my keyboard obviously. And the models are 3-dimensional, gas, steady. Why does everybody go segregated? I love my... Okay, constant density. It's interesting that you're using constant density, but I guess it doesn't matter that with constant density you're not getting any convection. It will be turbulent. And we're using K epsilon. Okay, if you say so, then we're using K epsilon. Yeah, then we're using gravity. I'm not sure who took these choices, but gravity and combined with constant density, I'm not sure if that makes too much sense. Because what can density, gravity do then? And Boussinesq model. Okay, close. Thermal expansion coefficient. Oh, we do have that. That's interesting. Air material properties. Gas, air, material properties. Thermal expansion coefficient. 33.3 E minus 3. Yeah, that looks like. And gravity. reference values. Oh no, guys. You made it in the wrong direction? True? Honestly? Okay. Epsilon is our new Z. If only I knew. Okay, that's done. Assigning continua to regions. Air, yeah, is air, obviously. Yeah, and that's solids. Yeah, okay. Setting boundary types. Boundary types. Regions, air boundaries. Air inlet. To stagnation inlet. Ah, that's this one here. Okay. Maybe I have too many of these. Pressure outlet. Maybe these should be combined. But who cares? I guess I have a bit too many things here. Maybe it's just this one here, not that one, but let's see. Okay, assigning materials to the multi-part bodies. Expand the regions, solid components. Physics values. Materials part group. Select the aluminum. And then go for GPU. Wait, GPU chip is silicon? Shouldn't it be silicon? Obviously it's not. Okay, GPU's heat sink block. It's not even copper? Come on. Plate. And the port blocks. Okay. All the capacitors go to alumina. Okay. Here we go. Okay. The fan casings. It's a plastics body. Okay, interesting. So the casings go to inlet fan, outlet fan, inlet fan, casing, outlet fan, casing. Ah, it's not the casing, it's just the fans. So what's wrong? Just give me a second. Okay. Okay, where was I? The PCB. Okay. And then we should have it. But what's about silicon? Ah, the memory chips go to silicon. Okay, good. PCB. And silicon will be the memory chips. Okay. Save the simulation. Yeah, I better do this. After that much of manual work. Setting up the heat sources. The heat emits, the GPU emits 25 watts. From when is this tutorial? Seriously, guys, 25 watts? Okay. That's a bit ridiculous. Maybe you can let me know what the TDP of your GPU is, but mine should be somewhere in the region of 200 or 250 watts, something. Oh boy, really? Okay. Select regions, solid components node, and say allow per part values. Yes, I did. Part subgroupings, yes. Rename subgroup to default. Yeah, defaults. Default. And we need a new one. New. And it will be memory chips. Memory chips. And in go the memory chips. Okay. This one is the default. And okay. Modify the physics conditions to accept total heat source as the energy source. So solid components, physics values. Set the energy source option to energy. Wait, what? Physics conditions node. Physics conditions. I'm dumb. Energy source options and say total heat source. Okay. Expand the physics values. Yeah. You can't read it. Expand the physics values. Select the heat source and say by part subgroup. Default is constant, none. Memory chips 32. What? Okay. Should I have created? Yeah. Another one. Here we go. And this is GPU. Okay. GPU. So we have that one here. Yep, there we go. And have 25 watts. Maybe I'm doing the same tutorial next time with some realistic. I always wanted to have my PC cooling simulated. Save the simulation. Yeah, did. Setting up the fan interfaces. 2 fans drive the flow inside the case. That's interesting. Fan interface. That curve. Okay. Expand the node interfaces. Case fans. And say allow per contact values. Okay. To internal interface, fan interface. Contact subgrouping. So we're Skolopos. Hi. We are doing some. Never mind, you can rewatch it. The visuals from the free surface are at the very start of the stream. We are now doing some tutorials around GPU cooling because I thought it might be nice to simulate how you GPU cool while your GPU is getting cooled in your computer, hopefully. Yeah, so here we go. Setting up the fan interfaces. Subgrouping 1, inlet fan. And subgrouping 2, outlet fan. And here we go. That's outlet fan, I guess. And the other one is inlet fan. Make sure that the okay, automatic, manual. Wilma, geh auf deinen Platz. Sorry, my dog's just barking because there's somebody by the door. Manual. Right click orientation and say reverse contacts. Okay. Each contact has an icon with direct arrow to indicate the this is so it's from upstream to downstream, and this one is from downstream to upstream, so we need to reverse this one. Okay. Select case fans, physics conditions, fan curve type to polynomial. Okay. Physics values node. Specify by parts subgroup true. Okay. Fan curve polynomial. What? Here we go. Number of intervals 5. And interval ranges. Yeah, I'm not reading this. I'm just copying it and pasting it here. Number of coefficients. Yep. Yeah. Now we go this. I guess you will have to. Oh. Exponents looks nice. Okay, set the operating ration rate to 1200 RPM. 1200 RPM. That's cool in STAR-CCM Plus, actually. You can just type in these units and it just takes them over and it understands what it's doing. Okay. Okay, so we copy this and paste it here. That was easy. Good. And all the other interfaces should be contact interfaces. Okay. Okay. Nice. So setting up the meshes. Now let's go to meshing. Oh, finally something that I do understand. What do you think, guys? Do we need a button to say just clear up my tree in STAR-CCM Plus? Just to have everything like collapsed again? I think we should have that in some update. So create an automated mesh for all the parts. What the hell? Surface remesher. Oh, I'm doing this separately. Definitely. Poly mesher. We need prism and we need thin. And then, okay. Measures, surface remesher, perform capability refinement. And I'm definitely going for 0.2 maximum quality here, like always. Yeah, I know. Automated mesh, default controls, core mesh optimization. Ah, yes, that's something that's really important that can really improve your mesh. I typically have higher values, but that's okay. Thin measure node 3. Automatic thin bulk shape detection. Yes, 3.7. That's actually the first time I'm using the thin measure. Okay, did that. So now base size is 20 millimeters, I guess. Prism layer control. Total thickness is 30%. Growth rate is 1.1. Maximum TED size is 140. That's interesting. That's not big. Okay. Save the simulation. Creating custom controls. Okay, that's next. Okay, parts. We need a block here. So, yeah, create close, whatever. GPU refinement, we call it. And we are just putting these minus 0.4. No, I'm not doing this. Yep, I know. Okay. Here we go. And here we go. Second one. Well, it's actually larger than. Yeah. Okay. And now we need it here. New volumetric control. And here we go. And then we have prism layer measure. Customize total thickness. and values 10%. Okay, that's interesting. New part control. For capacitors. Oh, come on. GPU chip, heatsink block, memory chip 1 to 8, PCB, plate. Okay. Thin measure. Okay, this one can be going down. Thin measure, custom, and customize thickness threshold. Yes, we're doing that. And values. Thin measure 4 millimeters, absolute. 4 millimeters. Okay. Then we need a surface control. Surface control. Oh boy, it's literally everything that goes into there. Nah, come on. To heatsink block, inlet fan casing, memory chips, outlet fan casing, PCB plate, and the blocks. So it's literally everything but the case. That's I'm not sure. So what we are doing now is custom controls, prism layers, disable, and target surface size, custom. We take what do we take here? So we are doing target surface size of 25%. That's interesting. I wouldn't have guessed. Save the simulation. I did. Generating the mesh. Okay, nope. Because now I'm doing a trick. I'm splitting the meshing between surface and volume mesh. So this is volume. Do I have? Yeah, and this is volume, and for the volume I go concurrent. For the surface I go concurrent. And I will disable the meshes right here. Thin, prism, poly. Okay, and here I will go parallel, and I will just to be honest, maybe it's per part meshing. Exactly, we need to make a hook here. And here I will just put the surface remesher away. So saving this one. And what happens if I click on, so now first all my processor cores individually mesh one geometry at a time. So, oh come on, that didn't work. for whatever reason. So we are doing it here again, putting the surface remesher here and just saying like that. Might take a little bit longer, but maybe we don't face any errors. Ordering patches. Yeah, looks nice. Looking good, looking good. Okay. Thing is that just didn't work is the individual surface mesh on every part. I thought it might be clever to let each processor core mesh a different part. That's why I opted for concurrent meshing and mesh per part. But turns out it didn't work, because sometimes then you have to sew these meshes together and errors can come up there. Yeah. So we just have to wait for a bit. And the mesh is also too small to be meshed by all processor cores at once. So this is why it takes a bit longer. I'm sorry. So then we can inspect the GPU. Yay! We can now turn on meshes. Mesh. And hide this one here. Now we can see everything here. Here. And let's turn on a clip. No, I don't want you to clip something. I will just clip through here. No, through here. And not through there. Maybe this one. And it's always the last one, that's correct. Yeah, that's just like how it is. Okay, let's see if we can move this plane. I want to see some thin meshes. No, we are not seeing thin meshes right here. Disable, come on. No, disable. Okay. We are cutting in the other direction, so here we go. Enable. We should be able to look at these. Yeah, it's just 2 layers. See? It's just 2 layers in these fins. Imagine if they had to be, or like more than that. It's also just 2 layers. That's cool. Imagine if they had to be isotropic. Oh boy. Okay, let's do this away. I have inspected my mesh. I may save my simulation. Yeah, nice. Preparing scenes for visualization. Yeah, this one we don't need right now. So, parts air case. A section plane I should prepare. Derived parts, new section, plane section. Input parts, okay, it's everything. Yeah, I will leave it at everything. Origin, 0.035. Here we go. 001, yes. New scalar displayer. Create and close. Okay. I'm gonna select a function. Ooh, we have something nice here. Blue, red, transparent. Do we have some Kelvin temperature here? Somewhere I had a cool Siemens Kelvin temperature. Maybe I can find it. Let me see. Color maps, yeah. Import color maps. Not here. No, I don't have them here. Oh, that's bad. That's bad. So maybe, here we go. Colors, colors, colors. Siemens color map collection. 76 color maps imported. That looks great. Kelvin temperature. Yeah, there is no Siemens Kelvin. Kelvin temperature Siemens, here we go. Yeah, but we need to revert that. Reverse, 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 and it's going to be 32. Yeah, that's okay. Let preference frame. Oh, hey. We shouldn't have a temperature scale here. We should have a velocity magnitude. So velocity. If it's come on, if it's just a 2D plane, I will do something different. Come on, clean it up finally. Derived parts. I will make a vector scene out of it. Line integral convolution. Here we go. Velocity magnitude, yes. And we can go for Siemens. Come on. Okay. In the temperature scene, we can put like all the other parts into there. Regions, solid parts. Here we go. And we should go to what? Temperature. And Celsius. Okay. So we should now have 2 in here. And the third one should be, what is it? Thermal conductivity tensor. Thermal conductivity. That's interesting. Never done that before. So temperature goes away. We need another color bar for that. We need, ooh, it's not like I have too many kinda alike fire. My dog is complaining. 2, 5, 6. Ooh, camera, hey, here I am. Kind of blurry for a second. And scalar field needs to be, what is it? Thermal conductivity tensor, then norm infinity, whatever this means. Okay, done. Deselect the following items. Okay, we should put some parts away here. Fan inlet, fan casing. Outlet fan casing. Block, yeah, nobody needs that. Why is it? It's putting the parts into that. I'm not sure if it can't be only the, like, the disc. I'm not sure. Misclicked. So, air case. We don't need air case. Air case. Everything where is air case, we just deselect. And air inlet, we deselect as well. Air outlet, we deselect as well. Block we don't have, and fan. That's all deselected. Okay, cool. Maybe that's what it should be. Okay, and once we're done with that, okay, so we are doing a maximum report. Reports user maximum. Max temp. Field function is temperature, I guess. Temperature in Celsius, please. Co-allocated future functions, none. Parts is, I guess, all solids. Yeah. Create monitor and plot. Okay. Modifying solver settings. Okay, it seems like we're getting somewhere. Really, we're getting somewhere. Fluid under segregation, segregated energy. Fluid under relaxation. 0.99. And here we do. Holy moly. Stopping criteria. Maximum steps 500. Save the simulation. Let's go. Here we go. Let's see. Ooh. That's not good. That's not good. What is it? TDR and TKE. Why the hell? It's always turbulence. What about the energy? The energy is fine. Okay. Let's see it. Let's check the temperatures. Hee, that's nice. That's actually nice. And that's even nicer. I like it. Oh, it's one of these old things where you used to have your power supply up. Holy moly, who built that geometry? Nevertheless, we might still have to work a bit on our mesh or something because my residuals don't look too promising and not too good. But for now, I'm wondering if I can read the fan speed. It was constantly set to 1200 RPM, I guess. But never mind. Okay. Meow. What's in my line integral convolution? It's a plane section and it cuts through the geometry as well. Okay, that explains everything. Oh, we're getting somewhere. We're stabilizing. Not that my residuals look any good. But it's comparable. Okay. At least it is fast. So, yeah. If that makes us happy. And really, guys, they are saying this as post-processing? Come on, we can do better than this. Okay. I'm gonna stop you right here. And we'll do some magic on the post-processing, shall we? Or do you want to wait until it's done? I am not sure if it's getting any better, but it's really getting hot in here. It's like 85 degrees Celsius. Holy moly. Amplifog, thank you. If you think that's looking great, that's the starting point for our visualization, to be honest, because that's my profession. Oh. Okay. What's going on? Periodic behavior? No, you're not. The thing is, we might assume our job is done, but the CFD engineers only start right here, right now. Because it's so much work from the first simulation that runs to a finely converging simulation. That's really good. Okay. So, but at least the maximum temperature plot is no longer oscillating too much. So let's stop here and make some parts look nice. So what's the thermal conductivity meant to be? Line integral convolution, you can go. Ah, that's our thermal conductivity of yeah, of our interface. Oh, it's only on the interfaces, you can see, I guess. Or did the no, it's the parts, and then you can see how much conductivity these parts have. Okay, that's interesting. I'm gonna correct this for a second because yep, and this goes out. Air case, air case, air inlet, air outlet, refinement, fan casing. Here we go. Yep. Okay. Looking good. Turning around the color map, reverse. Yeah, more something like this. Turning on advanced rendering, depth peeling, and this one here, and we need some metallic look here. Yeah. Okay. If you ever wondered what's the thermal conductivity, here you go. So, but we have played around long enough. Now it's time for some serious post-processing. So going back to our quality settings that are standard. Hey, Learned Machine. Hi, how are you doing? Thank you for the compliments. But the mesh is nothing but it's the mesh itself is just ugly. Okay, and it doesn't lead to good residuals anyway. So, thinking about what we should put into our post-processing. I don't want all these in here. I want just a few parts. I'm copying this one here to have only, let's start with the hot components, yeah? Removing that plain section for now. What happens if I put out all, first of all, the fans must go. Fan, here are the fans. Let's see, if I remove the fan itself, does it happen anything? Nope. So it's all, it's only, yeah, remove. Now you're gone. Outlet, remove this one. Nobody needs that. Okay. What is port block? Okay, it's just like a HDMI and display port. Okay, yeah, I see. So what we really want to have here is, so let's first hide all these and focus on the heatsink block. Okay, for now, because I want to find out hide. So that's the heatsink block that's left. If I hide this one, There's nothing in. Okay, that's interesting, because now that I know this, I can remove anything but the interfaces. Let me remove these, because they don't seem to have any. My dog is tearing apart my office. That's nice. Memory chip, we don't need, we only need the interfaces right here. So plate goes away, block goes away, block goes away. So here we go. That's for now. So we are calling this temperature metal. The color bar is not what I like for this occasion. I will go for something, oh, interesting, what we do, for something called cell heat. And it's wrong. It's more like that. Okay. And then we need some metallic. Yes, that looks more like it. We need, of course, more like maxed out, whatever you can get. Yep, that looks like it. Then we adapt the min max values. Okay, all regions. There are parts that are 26 degrees warm only. So we are doing like 30 to, what do you think, 85? No, we really need to peak out at 84, I guess. Yep, that could work. And we can put some more solid components in here. Do the capacitors have any? Yeah, let's put the capacitors. No, they are not metal, I guess. The memory chips are silicon. Maybe we can put them into it. Another displayer later. Come on. Okay. But the GPU itself goes into here. GPU chip. Yeah, sure. GPU. Where is it? Heatsink block. Here we go. Sure. The capacitors will be matte later. The memory chips are metal. Can we tune something in the metal displayer? Yeah, we could give them another. Okay. So let's for the overall visual impression, let's add the casing here. Parts, air case. Ah, now I know what kills my. Yeah, okay. Case. Case will have some constant. And it's gonna be some black, but lighter. Something like this. Okay. The front goes away. the interface goes away. And the other interface here as well. No, come on. What's this here? Oh no. Do I have faces for everything and anything in here? Yes, I do, obviously. Oh boy. So temperature metal. Oh no, really? Oh boy. So I guess it's easier to select what we want to show than what we don't want to show. So case goes to distinguish inputs first, and we disable this one, and now we select. Now we are just I guess it's top view. Now we take this here and select something like this. And rename them, call them a different name, and remove them from the displayer, from the case displayer. Ta-da! Then we can back to scene-plot. Let's say constant, temperature metal. Say shadows, and we put a metallic view, something on there, but make it rough. Do you want some clear code on that? Come on guys, you need shadows. It's like too bright from now, for now. Can we maybe dim the lights a bit? And make the background Wilma, geh auf deinen Platz. Hopp. Sorry, had to correct my dog. Gradient color, something like that in the lower parts. Yeah, that's more like it. So we could even make a glass front panel. So where is the PCB? Okay. I guess I'm putting the PCB in here as a surface. And I will give it a really old PCB-ish look. PCB. I will make it a constant and say, come on, you are a permanent green, or maybe this green PCB. You have shadows. You are matte, but you have a really glossy thing on you. And we have a metal backplate, I guess. Shall we put it into the temperature metal parts? Solid components. PCB. plate. Here we go. Ah, no, it's that one on the side. Don't we have a back plate? That's ridiculous. Okay. No, that's going to be, plate is going to be a new metal. That's plate. It's going to be preset material. The preset material is aluminum. And it does have shadows, yes. Okay. Here we go for now. So PCB is done, case is done. What else do we have? We will duplicate that metal thing and say it's these will be deleted. Remove the PCB, remove plate. You can go. The port block can be visible. The memory chip can be visible. The capacitors, or maybe the port blocks should be. Yeah, I remove them. I will put the port blocks as solid objects in here. Port. Come on, and they are gonna be golden. Extra fancy. Ports. Preset material. Shadows. Yes. Metal, gold, or maybe copper. Okay, and metal copy. We just make some different effects here. I will have something lighter as reflects. A little bit of clear coat. And some roughness, just to make it look a bit different. So, and the temperature scale should be gone. Color bar, scale, solid. Yeah, that's correct. Temperature, and we are removing the coordinate system as well because I don't need it and I don't want it. And now it's time for some lighting effects. Before we can do that, I need to have something in the new scene. New scene empty, which is the GPU chip. New surface displayer. Because I need to know where the midpoint is. Somewhere around this here. Yeah. Okay. So what we're doing now is making a transform, which is a scale. Simple transform scale 101, because I'm scaling by 1%. 1.01, 1.01, 1.01, 1.01. And my origin will be starting here. So the mid between these is 11.5, I guess. And 22 to this should be 16. And 23 to 27 should be 25.5 or 25.6. Okay. And now this is done. We can go back to our scene and duplicate temperature metal copy. Glow. And say we are doing 101 here. We are switching to light emitting. We are switching the color bar to not cell heat, cell glow. And we are decreasing the opacity to 0. And say it's more light emitting. And then we can take out the memory chips and the capacitors. Yeah, we are switching these parts. And say GPU. Here we go. And we say heat sink, because let's light it like that first. Now we need light on the GPU as well. Heat on the heat sink. Heat sink block. Selecting this one. Come on down to here. All you go. And here we go. Nah, maybe 5 is a bit too much, but 3 might work. I think that's nice. It's still a bit too much, you can't really tell the colors. So, did we... Looks like a night lamp. Yeah, a bit. We could also now add some streamlines from inlet to outlet to visualize the airflow. But the trick is, the important trick that I applied here is you duplicate your temperature displayer. You make yourself this scale. I focused, I set the rotation and scale origin to the point where the GPU is, so it's some centric point on the whole thing. And then I said, okay, scale 101. I made it a light emitting display, but said, please use opacity 0. Okay? And this is how it became, yeah, this glowing effect. Because it's not visibly visible itself, but like the it lights other surfaces in that case. Okay, cool, Amplifog. So I fulfilled my purpose with that stream. So let's see, we have 25 more minutes, and I will do some streamlines, I guess. First, turning off advanced rendering because, yeah, we don't need it right now. Streamlines. Streamlines are under derived parts. Derived parts, new streamline. Air solid components, that makes no sense. We are just doing them in the air. Part seed, select air inlet and add air outlet. New streamline display, yeah, I guess. Whee! Streamlines. Adaptive step. Maybe they should be. Holy moly, they are quite. Maybe I'm better setting them to the interface then. Come on. Then to the here and here. Okay. Inlet both directions. Both directions, I said. Okay, that looks better. Can we randomize? Yeah, that was worth it. Thank you. Okay. Streamlines, tubes, that's nice. What scalar field should we highlight on here? Make it temperature, maybe? That might be confusing. So we are going out at 68. We need to have a name it differently. Okay, but for now it should work. So putting that one just above my head. That's ugly. That's really, really ugly. Where is my Kelvin scale? Here we go. So we said 30 to 84, we said. 65 maybe. And then reverse it, please. Yeah, that's like a bad joke. Not so good. We should definitely make our own field function at that point. That's just like temperature. So we go for automation. So field functions, new, scalar. We call it air temperature. We call it, come on. Air temperature. Dimensionless, it's temperature, come on. And then we go temperature. And we can use it in our Streamline scaler. Ta-da! 30 to... Oh. We can do it 27 degrees inlet. And then we see some differences, and 67. Okay. And we can do some shadows here and make them transparent bodies. Now that's ugly. Make them matte, maybe. Make them have a clear coat, maybe. Nah, I think I gotta work on these streamlines. They are not yet perfect. And no, I don't like them. I don't like them. Maybe they are too thick. Let's see if I smooth them down. Maybe I should just go for velocity. Velocity, magnitude, here you go. And take another field function. What the hell did I do here? So no red, no yellow, if possible. No, that's not nice. So why did I say no red, no yellow? It's just because I think it's bad style if you have same colors in both color bars. It's okay to show two quantities in a single image, but it's not that cool if you show it overlapping with the same colors. Yeah, because then you have two colors meaning the same, and that's bad style, I think. But here we go. So, can I get a final vote on my image? I think it's okay for today. Maybe we should go for transparent body here. Increase the roughness a bit. Yeah. Oh, Amplifog. Don't call me sir, please. Okay. Okay. I guess that's it for today. I just noticed that I might have to work on my render settings, because every time I render a CFD image here while streaming Twitch, Twitch says to me, okay, your computer is overloaded. Maybe I should have just reduced the number of render threads to like maybe 30 or something. Let's see what it does if I turn it now. Nope, it's directly overloaded again. So 28 might do the trick. No, it still might need to restart. Or does it? No, it works. Fine. Nice. Okay, and with these findings, I like to conclude my today's session. Amplifog, thank you for chatting the very first time. I hope you liked it. I'm constantly trying to improve my sessions, so if you want to give me feedback here on LinkedIn, on YouTube, in comments, or wheresoever, you really appreciate it. Everybody else is as well. Skolopos, nice that you came back this year. And the Learned Machine, yes, of course, hi. Thank you that you're following, and thank you that you came back here. I hope you all have a great day. Rest of your day, start of your day, wherever you are. I guess see you next week. I'm not sure what we're doing then, but let's see. So good. Have a nice day. Bye bye.